Well, hello everybody. This is Pete Tatey from Pratt and Whitney. Welcome to our Process Control Methods Subject Matter Interest Group webinar today, sponsored by the Aerospace Engine Supplier Quality Group, one of the uh, key members of the SAE. And today's presentation involves the use of non-statistically based process control methods that are documented out of Reference Manual 13,006. This is our fourth webinar now in the last 3 months. And again, want to welcome you all here today from wherever you are. Hope you enjoy this particular webcast. Today, presenting will be myself, Pete Tatey. I'm a fellow in quality engineering at Pratt & Whitney. And hopefully Paul Gord, who's an engineering manager of aluminum operations and quality manager at PCC. Paul has been a member of this committee for the last several years. He helped to author AS 13,006 process control methods, as well as the reference manual, and as a member of PCC, Precision Cast Components. So today I'll give you an overview, and we'll talk about who the process control methods subject matter interest group is. I won't spend a lot of time on that, but just point you as to who we are and how we can help. Why this webinar? Where can you find help relative to process control methods? And again, we're going to walk you through the main body of this webcast is all about non-statistical methods. The last few webinars have been based primarily around statistically based controls, and we will continue to do that. But we also espouse non-statistical methods, and today begins that discussion. And also we'll go through some of the case studies that we've documented in the reference manual. And we'll close out with some Q&A and also let you know about some upcoming webinars. We've got some pretty good ones on the slate. So today, this webinar will be recorded, and you will be able to access the presentation material presented here along with viewing the video if you'd like to see it again, or if you have others that could not make today. It'll be available on the AESQ website past events page. Please use the chat feature if you would like to ask a question, and we will try to answer all the questions as they come up, or we'll reserve time at the end, as mentioned earlier. So the use of non-statistically based process control methods. Why this webinar? We usually, like to start off each one of these. Well, why? Why are we presenting this particular subject matter? How does it help you or us in that case? So the identification of non-statistical methods and when they can be used. What are the advantages and disadvantages of these types of methods? We want to show some practical applications, and we're going to have examples throughout. Promote the available free documents that are available to suppliers, to the AESQ, OEMs, and tools used by any of the AESQ suppliers. And there's plenty of them on the supplemental material page. We'll point you to where that is. And any questions that you may have about these types of methods. RM 13,006 is the main subject here, and this discussion comes directly from that reference manual. When we put that together, it was a strategic decision not to make process control methods all based on just statistical methods, but also non-statistical methods, in particular poka-yoke, or the Japanese word for mistake proofing. We'll be featuring that along with a few other techniques. So we want to raise the overall capability within our supply chain to understand how to drive the use of these process control methods that come out of the reference manual as a way to mitigate high risk from a PFMEA, and how to write better reaction plans on your control plan. So control methods and the reaction plans go hand in hand together. Now, the reference manual was developed by a dedicated team here of process control professionals that worked several years in compiling this excellent information. And along with this reference manual are many others available for free on the AESQ supplemental page website. So what is the subject matter interest group? This is a group, as mentioned, of the process control experts. We get involved in the AS 13100 content when it involves process control. Reference manual content, we own that. We're in the process of looking at ways to improve that reference manual right now. So we get together on a regular basis. Every 2 weeks we meet and we go over changes to the reference manual, webinar subjects, and what is it we could do to help the supply chain in this area. There is a community of practice that we sponsor on the LinkedIn social media site, where you can go on and ask questions and we can get back to you with answers. Here is on the lower right, a list of future webinar topics. After today, we'll be driving in April, the power of pre-control. Andrew Stout, our co-lead of this SMIG team, will be the main presenter on that. I'll be following that up in May with the 1-hour process control assessment. And so then we will be setting up the next half of webinars for the remainder of 2023. So again, a busy schedule. This is the membership of the SMIG team for process control methods. Again, members from each of the key member companies for the AESQ. And the community of practice site, again on LinkedIn. Here is the URL that you can go on to and become a member. Please join us. Join our LinkedIn site, ask questions. We post a lot of interesting information relative to process control and future webinar schedules. So excellent site to be informed on what's going on process control wise. We currently have 175 members. After today, I'd love to see that go over 200. It's growing every time we have a webinar. It goes up about 20 or 30 people. So now we're going to take a walk through non-statistical process control methods. A lot of this is directly out of the reference manual with some supplemental visuals to help enhance the learning. So let's give an overview of the recognized control methods. What's error proofing or mistake proofing all about? Run charts with non-statistical limits, life usage, techniques, visual process check and checklist, first piece check, and test piece evaluation. I see my cohort in crime is now on, Paul Gorg. So he must have managed the technical difficulties. So I'm going to turn it over to him after this particular slide. So what is process control? We've defined it here to be very strategic And again, overall, a broad definition is to employ and reduce the strategy to employ and reduce and mitigate product and process risk. So it's something that results out of a design or process FMEA. Those are the tools to identify risks and also the control methods to help mitigate those risks. Process control includes here the use of statistical and non-statistical methods. Okay. Again, these are to work to prevent and detect errors. And we know from design and process FMEA, the way it's structured, the columns are there for prevention-based controls and detection-based controls. We're going to key in on the prevention-based today. We'll talk a little bit about detection as well, but the initial discussion will be on error proofing, which is more driven towards the prevention. Non-statistical techniques can include a lot of different strategies, mistake proofing devices to control inputs that generate outputs. It could take the form of like using asymmetry in a design of a part to help locate it one-way fits, buzzers and alarms that signal that you've entered an error state and then follow the reaction plan to get out of it. Work instructions, of course, standard work checklists, qualification processes around setups, and pre-control, which is subject of next month's webinar. Those are a few of the non-statistical techniques sponsored by Reference Manual 13,006. So again, it can be statistically based in the lower left or non-statistically based over here toward the right. One-way fits, guide pins, error detection alarms, checklists. Those are some of the non-statistical methods. So, Paul, are you on?
I am. I apologize. I ended up having to get my local and my division IT to figure this out. So we got it.
Well, and you did that in that amount of time? That's pretty good.
Yeah, went and grabbed him.
Paul, welcome aboard. I'm going to now turn it over to you if that's
Thank you.
okay.
So on the previous slide, I guess one thing that I wanted to, point out as far as non-statistical methods is there's a lot of different tools, and a lot of them are going to be particular to your business and what you make. I mean, it's somewhat less structured than a control chart or a statistical method. There's a lot of things that will apply specifically to what you do, and you're the expert in those areas. So it's kind of one of the reasons I like it as well. All right. So we wanted to reference some of the materials that are out there. There is some there's a lot of information on mistake proofing out there. What we're going to talk about is why non-statistical methods, when they're applicable to use, and then go through some methods and some examples. The pokey oak is, everybody's kind of familiar with that name, or mistake proofing or error proofing goes by a lot of different names, but it's not the only thing we're going to talk about today. But you can use this as a reference material and where to find it. The goal of is basically to prevent the cause of the failures and the defects. So that's what we're trying to do. Okay. So when to use process. First of all, when the process can be error or mistake proof, when the elimination of the actual defect is possible. If the process does not easily lend itself to statistical methods, either the data is not normal, we'll take a bunch of, we'll have to, go through transformations and all that kind of stuff, then it's going to be very difficult, it could be difficult to use statistical methods. The other advantage is it's easier for operators to understand and accomplish it can be done on the shop floor. And the other advantage of it is to give you immediate feedback at the operation where you're doing it. You don't necessarily have to wait for data analysis, and it may be less expensive to the organization overall to accomplish. So, and key kind of can be simple and fairly easy to understand. When not to use, you may be in a situation where your process data is easily attainable. You have a nice normal process, it's easily collected, then probably your statistical methods may well be the what you want to go. If you have non-statistical methods, they're not going to give you process capability metrics if you're needed for the customer or organizational requirements. It's not going to give you a CP or CPK. It's not going to, you're not going to, necessarily have that type of data if it's necessary. And my typo is still there. Data is needed for process development improvement. So in a lot of cases, the non-statistical methods are going to be more accept, reject, go, no go. So if you have a need for incremental data to look at process development and process improvement, it may well not serve that purpose. Next. So this is kind of basically showing that all this kind of flows, right? The key goal of the process control is to help mitigate risk. Non-statistical methods such as mistake proofing is applied for the highest PFMEA. And what we're trying to make clear here is, part of this is you do your PFMEA, you generate your control plan. The control plan is based on your highest risk items from that PFEMA. And in a perfect world, your mistake proofing would be applied to your highest risk, meaning how do we eliminate the number one highest risk on that PFMEA from occurring? Second would be, SPC. Third would be, okay, let's inspect it, set targets. Fourth would be audit. And, those might be acceptable for lower risk, but, the higher the risk on the PFEMA and into your control plan, the more you want to try to generate something that actually stops it from happening. Like I mentioned in the first slide, there's a lot of different ways you can do this, and a lot of it is dependent on your process and what you're making, but goal is to, use your ingenuity, use your ideas, use your teams, figure out what can be applied, but to eliminate the defects 100% of the time. So it's a little interesting in terms of there's kind of two aspects of this. One is there's error or mistake proofing, but an error doesn't necessarily mean a defect, but the goal of the mistake proofing is at the highest level is to eliminate that error, to make sure that error can't happen. So why does it happen? Forgetfulness, misunderstanding, lack of experience or skills. We're dealing with a lot of new people in our industry right now, a lot of training, lack of standards, trying to get things out fast, malicious intent, but that's extremely rare, and errors that lead to defects. Defects are not always inevitable, but you get limited by use of simple low-cost methods. So repetitive mistake proofing is best applied or can be applied where there's repetitive tasks that depends on somebody doing the same thing every time, remembering to do something. Those are more applicable areas for it. Ed? So we're talking just a little credit to the father of it is this gentleman, Mr. Shingo, who's attributed to developing the method. Originally called, we've all heard it over the years, idiot proofing, but decided that was potentially offensive, so changed it to poka-yoke, which is to avoid inadvertent errors. And the target of it, and why we want to do it, is to eliminate QC inspection, to reduce costs, basically to make sure that you don't have, you've eliminated the potential to even have the defect, so you don't even have to inspect for it. Go ahead. So errors, and again, this is kind of a little different in that the errors are, this kind of just a summary of the potential errors, and some of them are going to be applicable to your process, some aren't. Errors don't always create defects, but often do result in defects. Mistake proofing in its best form is going to eliminate the mistakes from happening, thus eliminate even the potential for a defect. So, and we'll get into the levels and rankings on mistake proofing, but the best one is going to actually eliminate the potential for that defect to even happen, or that error to happen, which will eliminate the defect from happening. Go ahead. So defects, omitted processing errors, error setting up a workplace, missing parts, wrong parts. You guys can read through the list, but these are the product defects. And again, sometimes the mistakes won't generate a defect, but sometimes they will. And if we can eliminate the error, then we're going to eliminate, or the mistake, then we're going to eliminate the defect. And again, we'll go into more levels on this next. So error proofing can take, 4 forms, and this is kind of a hierarchy. The one best is the elimination, to design the product or process in such a way that an error is not possible, that you can't make the mistake. The second one is control, and you may not be able to stop the error from occurring, but you can make sure that it doesn't move any further through the process and that the defect is going to be 100% detected. Not quite as good because it doesn't actually eliminate the error from being made necessarily, but it will eliminate the defect from moving forward. Number 3 is provide an warning signal. So it detects the defect, gives an operator warning, but again, it or error, again, though it's going to show that it doesn't necessarily stop it from happening, but it does give you the ability to deal with that and fix the situation. Facilitation is worse, but and we're familiar with those. Those are work instructions and procedures and guidance, trying to increase the likelihood that we will catch the defect or the mistake before it turns into something worse. And again, this is kind of just another way to look at it, but the best one is level 1, which eliminates the mistake and defect from occurring at the source. So, example over there is the plug that, you've all seen them with the bigger tang and the smaller tang to make sure it only goes into the socket one way and guarantees polarity. Level 2 is, defects are going to be detected. They're going to be determined and found, and alerting the operator. Method 3 detects it, stops it from further processing. So examples, it'll be a little easier to look at examples and what we're talking about here. So on the first example down there, the operator has a choice of where to put the tube in this assembly. There's 2 locations it can be. And so the instructions, I'm sure, told him which location and where it was supposed to be, but there was not anything from stopping him or her from putting the tube in the wrong tube. So the error proofing to this with the level 1 is to add a feature to that fixture that physically will prevent them from putting the tube in a wrong location. Mm-hmm. The defect, again, is not possible. It can't be done with this type of situation. So this is a level 1. This is where we want to end up if at all possible. And with this, then nobody has to worry about inspecting it, looking for it. It's guaranteed. The next example is kind of a level 2. So in the example here, there's one screw that needs to be installed, which is a different size than the rest because of the cutout at the bottom. The screw can still be put in, and so the error was starting to be made, and that they could put the wrong screw in that slot. But the error proofing on the level 2 on this is that if they put it in the wrong spot, the screw will not go in and will be exposed, noticeable, will be clear to the operator. So it doesn't fix necessarily the initial error, but it does fix the defect and make sure that this can't be, will be obvious and visible and not be able to be moved forward. So this is a level 2. And level 3 is, again, the defect can be made, is caught, or the mistake can be made and the defect can be made, but the jig itself is a inspection method basically that is going to tell the operator whether that defect was made. So it doesn't stop the mistake, it doesn't stop the defect, but it stops the defect from, it contains it, keeps it from moving forward. And, you know, because that non-pierced part can't go through that pin. So, you know, it accomplishes the goal of not letting the part go forward. However, it does not eliminate the error or the defect. So still a good thing, but not the best. So these are just some additional examples. I mean, a lot of us have dealt with fixtures and tooling where we, you know, put in different size guide pins, put in diamond pins and a diamond and a round and things like that, or so the things just can't be assembled together incorrectly. They won't fit. We have alarms that either light or sound or you know, in the best cases, that actually shut down the machine if something is not to enter parameters, limit switches, so that the tooling is lined up. You know, there's a lot of things here. You know, lower level mistake proofing is going to be a checklist that you know, make sure it's got to be signed off. And we'll go more into checklists later. But it's got to be signed off, got to be acknowledged. You know, in the best case on checklists, there's 2 people looking at it, so you've got a double check. Anyway, I think, you know, most people have examples in their business of other methods. Right. So control charts, non-statistical control charts. In our business, I'm in the casting business. We use a lot of run charts because you know, particularly in our investing or shelling process, it's a ongoing chemical reaction. So we have, you know, in the case of a run chart, you can have set points and limits in a defined plan, so that when you get to that set point, actions need to be taken. So this is going to lend itself to where you don't have a statistical valid process. In our case, we're making additions, we're making chemical adds, water adds on a shift basis. So it doesn't lend itself to doing a statistical analysis or doing control charting per se with calculated limits. So we define set points, and set points have, then when we hit those set points, there's an adjustment that needs to be made. There's a lot of opportunity for control charts in non-statistical. It's the advantage of these is they're pretty easy to use. A lot of times the operator can enter data. It's a clear limit. When they hit that limit, then there's a defined reaction plan that, okay, this is what I need to go do, and then retest the data. If I'm back within my set points and where I need to be, then I can continue processing. So, you know, it's a convenient thing to do, simple, easier to understand. I'm going to let Pete talk a little bit about pre-control, although like you said, he's got a additional seminar coming up on that.
Yes, we do, Paul, next month. And but pre-control is a non-statistical technique. It was created back in the 1950s when you didn't have calculators and computers on the shop floor. And it's a simple technique that basically says take 50% of the tolerance, the inner 50%. That's your green zone. And it's used to help prove out a setup and then used as a monitoring mechanism during the production of a lot. So proving out the setup, get 5 parts in a row in the green zone, and then you check every 5th part or 20% inspection frequency. Get 2 in a row in the yellow, that tells you got to shift, make an adjustment. You get 1 in upper yellow zone, and then the next part is in the lower, you got a variability problem. So it's used to help qualify a setup and used to monitor a production run based on the spec limit. It's not based on statistical limits, it's based on the spec limit. But it does assume the process is capable with a CPK of 133 before you use and deploy pre-control. More on that next month. I'll leave it there.
So some general advantages to some of these type of control charts, particularly the run charts. No prior statistical knowledge required for application. They're fairly easy to use. They're fairly straightforward. You have the data, you have a set point, you have a reaction plan. It's fairly, like I said, a simple, operators can do it. A lot of times it's best applicable to systems and processes that are easily measurable, right? You can measure them with a micrometer or we use a viscosity measurement or something the operators can do and they can enter. Disadvantages is the set limits, warning limits are based on, you are making an assumption. Now it's important that assumption be based on data and some, some knowledge. You can't just they won't do any good for you if you set a limit that is going to yield bad product and doesn't actually control your process. So you have to be smart about where you set your set points, what they mean. Does take some knowledge. Doesn't yield anything in terms of, what are you actually getting for variation? You're just going to see typically a run up and a intervention, and then a God back and going to go back down. Doesn't really give you yield itself to getting a lot of data for cause corrective actions. Possible applications, and this is where we use a lot, is directly at the work center as part of the work. The worker themselves, the operator, does these checks, and then, like I said, has a reaction plan and is able to make that corrective action immediately right there at the operation. He's not waiting for anybody to analyze anything or come back. Run charts for work on non-normally distributed processes. The other thing they can be used for is in processes that it cannot be produced capable. So, there's kind of 2 examples here. One is where the spec limit or the set point is very close to the control limit. You're not going to be capable. So, maybe you need to set your spec limit or your control, not your control, but your set point tighter, and make sure that you have that reaction plan. In the other case is if you have a large CPK, but you want to control, you don't really want to control it to the CPK limits, and you'd like to control to a tighter specification, a tighter set point control limit, then maybe you use it in those applications well, where you actually want to use something that's tighter. Okay. All right, so life usage control is another one. And, you know, I think a lot of us are familiar with this. Big example is we all change our oil on our car at a certain time and point. So many processes have a factor that are, you know, change over time or over the number of pieces made. And this basically is defining where that condition is that's going to adversely affect a product or process. And then we place controls on those. So typically, you know, for age, a lot of us, if you deal with coatings or adhesives or that type of thing, there are age limits on those. There's pull-by dates. There's, you know, you can only store them so long, or they can only be, they have to be at a particular temperature. Maybe a number of parts produced. Some tooling isn't going to need to be replaced after a certain number of parts, certain number of runtime. Again, once it's open, the use-by date, weights. I mean, sometimes there's max weights on parts and things like that, and that help you determine if you're within where you need to be. So again, this you need some data. You need and some of the stuff is going to just be a customer requirement or a product requirement. Some of it you need some data to understand what you need to set ideally to maximize the process quality. You can't just set an arbitrary number out there. You need a little bit of data. And again, ideally, you'd have some statistical studies and experiments that are going to tell you what those numbers are. And then, you know, make that part of your reaction plan or your procedures and what you do there. Yeah. So examples: cutting tools has a maximum operating life. Tool life is recorded in a machine readable chip. I mean, in that world, sometimes it's very calculated in hours or time, and then the cutting tips are replaced. Peening operations is based on total equipment running time, you know, how much uptime on the machine, how long it's run, and then when the media needs to be changed, determined by that time. Ideally, what you'd want is you'd want an automatic shutdown on the machine so that it stops at that point. Not just a warning light or something like that, you know. Then in a perfect world in this, you'd actually have a hard shutdown. You know, we do a lot of etching in my business. We take, you know, there's so many months or days or that we can use an etchant. Also measured, another way we measured later on in test pieces. But, you know, when do we need to control that? When do we replace the acid? When do we place the concentration? Sometimes, you know, this stuff is easier just to set a date and just do it routinely, rather than try to go through all the effort of determining, like, you know, like an example here, every Monday morning we're going to replace it. Or it may have you know, you may check it, get data like I'm talking about, and then decide on the etch, and then decide whether you can reset and continue to wear it, continue to use it, or it needs to be changed and removed and thrown out. So just a few applications. So another one is visual process and checklist. This is kind of you know, down the bottom of the list in terms of the mistake proofing and you know, but something we do a lot, and that is that, you know, something that's not easily measured, like is appearance nature, so visual criteria, things that are difficult to measure and are somewhat subjective. You know, you can develop checklists, visual inspection. Recommended that it's not a single person check, and obviously it's not the person that, if it's a manufactured operation, it's not the person doing that operation that is necessarily checking that operation. So if you can do a double scrutiny, you may basically have two people look at it to confirm or check that it really is conforming, then that is a good way to do it. If you can do it nowadays, I mean, there's all kinds of stuff that's coming out with visual and scanning and a lot of automatic methods now. That certainly would be ideal. Process checks need to become part of a routine operation. They need to be a formal checklist, ideally, or a routed operation, something that somebody has to sign off on and acknowledge. And obviously, we need to do enough training as an organization to make sure that people understand what to do if they fail against that, and the importance of it, and what they're actually looking for. These can be difficult because sometimes the criteria is not, especially in terms of visual applications, is difficult to interpret. So it does take some training, does take some skill there, and some real work on definition as to what is acceptable and rejectable. Go ahead. So an example, this is a pre-operation, just a checklist. So in this case, the part number is identified, the process number, when it was done, and the steps, and they require a pass-fail and a sign-off. So ideally, the individual would look at it, they'd sign it off. Some definition of a reaction plan is on here. If they have a failure, is what to do with it. And then I would say, one addition to this, it's not on here, but you could have a cosign on there here as well. Another example would be something as simple as, we counting nut plates or rivets, and then recorded in the IT system. We have a lot of stuff here that is on our what we call our EPMS system, our router system, and we're able to put in a prompt where after the operator completes the operation, they have to enter data into the system or they can't move it forward. They have to indicate, okay, I've got 24 net plates, or I checked the rivets, and the count is, and unless they enter the data, accept that operation, the part can't move forward. So that there's a lot of, with people going more and more to electronic systems and away from just paper routers, that is a good opportunity nowadays. Okay. First piece checks. I mean, this is kind of old school, but it's still very important. Especially in a machining operation or for other applications. Basically, finish the first piece, make sure it's checked. Do dimensional checks if you need to, or visual checks. You'll have to determine what it is you're looking for, and then determine, is that acceptable before proceeding with the remaining operations. Ideally, it's going to be done by somebody that is not the initial first piece check is going to be done by a second employee. Maybe it's a second operator. It doesn't necessarily have to be an inspector, but it's potentially somebody other than the person that is doing the operation, just so you don't have that potential of, we've all been in those situations where we made a mistake. You keep looking at it. Because we made that mistake, we keep thinking, nah, this is fine, and you just don't see it. Whereas somebody else will walk over and say, yeah, it doesn't look right. And some of the best cases is if you can use a different inspection method or a different tool, just in case you've got a measurement problem, a tool problem. And again, going back to kind of the previous on the checklist, part of this is you can use a similar sort of checklist on this to where that first piece inspection is documented, is checked off, is acknowledged in the WIP or EPMS system, so that you can verify that was done. Okay. So examples: first piece check with known adequate, comes over, checks it, it's looking for 50% of the tolerance. if it's not within those limits. And again, it's important to have defined limits as to what what your action plan is. If it's not within those limits, an adjustment is made, an additional piece is done, and that's checked. If that is able to go forward, then within the limits, and then you keep going. Products that have an upward drift, again, first piece check. Again, important to have a limit in terms of what your action plan is. If it's inside those limits, and then you keep proceeding. And sometimes on this, you may need to have a periodicity. You may have to say, okay, I'm going to do the first piece, and then I'm going to do another check at the 25th or the 50th if you're really seeing a drift. And I guess one note on this is example 2 in this uses other statistical methods or non-statistical methods to set the defined limits for the first piece. So they're using a run chart to look at it, or a toolware study for life. So a lot of these tools can be used together and lend themselves to each other. Test piece evaluation. There's a lot of things that are difficult to measure directly on a part, even mostly because in a lot of cases we ended up destroying the part. So use of test pieces alongside the product may help, is a tried and true method to determine its process and its stability. And in a lot of cases, these are driven by customer requirements and are necessary for validation of the product. So, examples for those, and this is, a hardness tester over here. We do hardness testing after heat treat to make sure that the parts were heat treated properly. And surface, again, hardness testing for shot peening to make sure that was correct. In my industry, everything runs with test bars for mechanical property testing, again, to verify that mostly that the heat treat was done properly. We pull coupons at melt to verify that the chemistry is done properly. In etching processes, there's test coupons that are used to determine the etch rate, or even in electrochemical polish as well. So there's a lot of use in this. And again, a lot of times they require customer approval, and a lot of times statistical methods are used with the test piece results. We'll run CPKs on our test bar results, and we'll look at chemistry distributions and see if we need to adjust anything. So common in our industry for a lot of applications. And again, this is something from my industry in terms of we pull test bars and 1/4-inch rounds and have customer defined mechanical properties that are required, and the part have to meet these properties, and these go on this. A lot of times your test piece data will go on certifications, will be requirements for shipping product. So I guess the biggest thing for me, again, is there's a lot of different non-statistical methods, and they're going to be very much applicable to what you're doing in your business and your product. So don't be afraid to suggest something, use something. The biggest thing is to have the data back it up. Why you're setting those limits, why you're using this method. But I think there's a lot of value in them. They're easier to, I think for the most part, they're easier to understand, easier for people on the shop floor to do. Data can be collected very quickly and acted on very quickly. So I think it's an important part of our toolbox. So with that, go on.
All right, Paul, thank you so much. Now we're going to start winding it down, folks. Future webinars, this is the schedule. If there's a subject that you're looking for that's not on this list, again, feel free to go on the Community of Practice LinkedIn site and let us know what you're looking for related to process control methods. A lot of these subjects we came up with a poll. We'll probably come out with another one again as we start driving toward the second half of the year. I can't believe I'm actually saying that. But again, so far we've had a very good run here. We've got many more on their way. So are there any questions at this time that we can take?
Pete, we don't have anything in the chat box that I see right now, but let's give everyone a minute to get into the chat and type in your questions in there.
Okay.
So I'm not seeing any typing. This is a quiet group we have today.
It must be hungry.
So I think we can go ahead and wrap it up if you want to.
Okay, that's fine. And so all resources again, this video recording as well as the presentation itself be available on the AESQ website within a few days. If you give it a week, it'll definitely be there for sure. And an email will be sent out to all registrants with the link to get at the actual recording. So with that said, I want to thank all of you for attending today's webinar and look forward to seeing you again. Please join the community of practice and have a great rest of the day, everyone. Thank you very much.